Okay, I'm going to talk about waves today. And waves, it's a new unit we're starting. And wave, this is a definition right here, if you don't notice that. This is a definition. It's a disturbance that transfers energy, okay, through matter or space, okay? And we're going to talk more about that. There are two types of waves. And I'll let you read this on your own. I'm not going to cover everything. I'm just going to cover the high points. Electromagnetic waves. Sometimes we call this electromagnetic EM radiation. It's what we commonly refer to as light. Okay, although it also includes things we can't see that aren't visible, like gamma rays, X-rays, ultraviolet, infrared, microwaves, radio, and so forth. Okay? These waves do not require a medium. Okay, they can be transmitted through a vacuum, like, for example, space. We get energy from the sun through space, and that's electromagnetic radiation. It's transferred through a vacuum of space. The second wave is called a mechanical wave, and a mechanical wave actually mechanically travels through matter, and that matter is called a medium. Okay? Okay, and that medium is defined down here. It's a substance or a region through which wave is transmitted, and it transmits wave energy, okay, but doesn't actually have any overall motion itself, okay? But it's transferred via matter, the medium, okay? And a couple examples are ocean waves. They have water for a medium, and sound waves, which have air for a medium. Sound can also travel in water and solids too. All right? So those are the two types of waves, and this is a definition for the material through which mechanical waves travel, mediums. All right? Okay, let's keep going. So waves are about energy transfer. Waves transfer energy. Okay? So this talks about how you can define what's a wave and what's not a wave, and I'm not going to spend a huge amount of time on that. But let's talk real quickly about wave movement. How do waves move? Well, they move, there's two primary types. One's called a transverse wave, and one is called a longitudinal or compression wave, either one. I like compression in some ways because it's easier to understand. A transverse wave, it's defined where you have the direction of the energy this way from the left to the right. That's the direction of the wave that the wave travels. But the motion of the wave material, the motion of the material is perpendicular to that. So for example, if you had a slinky and you created a transverse wave, well then the medium that the wave's traveling in, the slinky, would move up and down. Okay? But the wave would actually travel from left to right. Okay? Now there's a couple examples of this. Light is one example of a transverse wave. That's the big one. And ocean waves are another example of a transverse wave. The water moves up and down, but the wave moves forward. All right? The other kind of wave that's very important to us is what's called a longitudinal or compression wave, okay? And that's where the molecules of the medium move in the same direction or parallel to the direction of the wave itself, okay? So that the waves are a series of compressions and refractions. So the compressed zone is where, this is a slinky again, okay? The compressed zone is where the slinkies close together, and the rarefied zone or the rarefaction zone is the area where the slinkies spread apart. Okay, this is close together, and this is spread apart. Okay, now as the wave moves, the waves push this way by a force. Okay, the movement of this wave is from, again, left to right. But the compression takes place as it travels. Okay, so another way to look at that, this is in the air. You have air molecules which are close together, and you have air molecules which are far apart. And the sound is propagated this way. Okay? Two really great examples. So compression Compression is the space in the medium in which the molecules are crowded together, and rarefaction is the area where there are fewer molecules. The best example of this is sound. Okay? So sound causes the molecules of the medium to vibrate back and forth and to compress and rarefy, compress and spread, close and spread, be close and spread. All right? So for this wave, the best example for a longitudinal compression wave is sound. The best example for a transverse wave is light. Sound needs a medium to travel in. Light does not. Light can travel in a vacuum. All right, let's keep going. So what are the three basic characteristics of waves? Well, if there's no wave in the medium, this is a medium, okay? And in the top, this would be, we're going to assume this is water. Okay, this is a water wave, all right? And on the bottom, we have a slinky. Okay? Okay? So this position in the middle then, if the water didn't have a wave in it, this would be what was called the normal rest position. Another name of this is the equilibrium position. Okay? So the amplitude is the maximum distance the molecules of the water are displaced from their normal rest position. Okay, amplitude indicates the amount of energy of a wave that's a transverse wave. This is the amplitude. Okay, so is this. These are both amplitudes. Okay, and this is an amplitude. All right. Higher energy is indicated by a tightly compacted medium. Okay, so this is tightly compacted. Okay, tightly compacted. Higher energy. Okay, higher energy is also related to amplitude. Frequency is a really important concept, and that's the number of complete waves or cycles per unit of time. Okay, and that unit of time is a second, typically. And also another way to say this is waves or cycles, oscillations. So it's oscillations, waves, or cycle per unit of time. And the unit for that is hertz. So another way to say hertz is 1 hertz equals 1 cycle or 1 wave per second. Okay? Okay? The period, this is t, and that's equal to 1 over the frequency. The frequency is f. Okay, little f. Period is big T. Period is the time it takes for 1 cycle. Okay? That's the time it takes for 1 cycle of the wave. Okay? So let's do a little quick practice and talk about that for a quick second. Okay, practice 1. If you move a jump rope up and down twice in 1 second, the frequency would be 2 hertz. Well, let's talk about how that is. If you move a jump rope up and down twice, that means 2 cycles in 1 second. Well, that equals 2 hertz. All right? Okay, the speed of a wave, this is called what I call the wave equation. Okay? The speed or the velocity is determined by the number of waves passing in 1 second, the length of the wave. All right? So let's talk about that for a minute. The velocity of the wave, v, is equal to the frequency, f, times the wavelength, lambda. All right? Okay, and so this is how you describe the equation. This is it right here. So v is the velocity. It's in meters per second. That's the speed of the wave. F is the frequency. It's in hertz. Okay, that's the number of waves or cycles per unit of time. So this would be like cycles per second. And the wavelength is in meters. It's the length of a wave. Let's back up and talk about that for a minute. Okay, so we talked about the amplitude. Here was the amplitude. Okay, the distance from crest to crest of the wave, 1 complete cycle, is called the wavelength. okay? The distance of one complete cycle of the wave. Okay, from here, from crest to crest or trough to trough is called the wavelength, and that's described by the Greek letter lambda. Okay? Okay? So that's the length of one cycle. Okay, the length of one cycle. Okay? The speed of the wave depends on the medium. Okay? And amplitude has no effect on speed. Okay? So if you look at the comparable, let's go back to the slinky again. We saw the amplitude here. The distance between the two compression zones in the slinky are also the wavelength. Okay? They're also the wavelength. All right? Okay, let's move on. Okay, so practice 2. Since speed is constant in a given medium, if the wavelength increases, what happens to the frequency? So the velocity is equal to the frequency times the wavelength. Okay, so if the speed is constant, so this v is going to be a constant number. Okay, if the wavelength increases, so this is going to increase. What's going to happen, and if this is constant, in other words, if the product of frequency and the wavelength is constant and the wavelength increases, then the frequency has to get smaller. It has to decrease. What happens to the frequency? F decreases. Okay? Practice 3. A sound wave has a frequency of 110 hertz and a wavelength of 3 meters. What is the speed? Well, velocity equals the frequency times the wavelength equals 110 hertz times the wavelength of 3 meters. So the velocity is 330 meters per second. Okay? Okay. Okay, so practice 4. Here are a couple of graphs. One is the height of the wave in centimeters times the time. And one is the distance that the wave travels versus the height. Okay, at whatever distance, what is the height of the wave, right? At a specific distance. Okay, let's talk about this. The wave's motion is graphed as a function of time and distance. Okay, so what is the wave frequency? Well, the wave frequency, F, okay, is the number of cycles per unit of time, second. Okay, so let's look at the time height graph. How many cycles do we have? Well, start here. This is a crest, down, and back up to the crest. That's one cycle. That's one wavelength. This is one wavelength right there. Okay, that's one cycle, right? Okay, so what's the wave frequency? Well, there's been one cycle in 1 second. So the frequency is one cycle in 1 second. So the frequency is 1 hertz. Okay? Okay. What is the wavelength? Okay, so let's go over to this side. We want to cycle again. So we started here. We go across. We go down to this point. That's one cycle. Okay, that's one cycle. This is one wavelength again. Okay? So what's the wavelength? Well, one wavelength is 5 centimeters, or 0.05 meters equals the wavelength. Okay? What is the amplitude? Well, you can see that it's the distance from the resting position for both of these, and you can see the amplitude here is 10 centimeters, or 0.1 meters. So let's calculate the speed of the wave. The velocity equals the frequency times the wavelength. Well, the frequency of this wave is 1 hertz. The wavelength is 0.1, oops, made a mistake there. The wavelength is 0.05 meters. So the velocity of this wave is 0.05 meters per second. That's the velocity of this wave. All right? Okay. We'll talk about the next section on sound in just a second.